Welcome to ECO 442, Study Session 4, Linear Programming 3, Further Consideration. Introduction. In the previous two lectures, you learned how to set up a linear programming problem and obtain solution either graphically or by simplex method. In this lecture, we will consider some special topics about linear programming problems. These include the problem of multiple solution, infeasibility, unboundedness, and duality. Objective. At the end of this lecture, you should be able to write the dual of a linear programming problem. You will know how to identify when solution, a linear programming problem suffers multiple solution, infeasibility, or unboundedness. A. Multiple optimal solutions. It is possible to have a situation where there is more than one optimal solution. In such a situation, each of the multiple optimal would yield the same value in the objective function. This happens when the slope of the objective function, also called the isoprofit line, is the same with that of a constraint. The objective function is parallel to a constraint that forms a boundary on the feasible region in the direction of optimal movement. In a simplex method solution, a LP problem will have multiple equilibrium when values of triangle J for all non-basic variables are 0 at the optimal solution. B. Example 1. Two optimal solutions. Use graphical method to solve the following LP problem. Maximize Z equals to 8P plus 16Q, subject to P plus Q less than 200, Q less than 125, 3P plus 6Q less than 900, P, Q greater than 0. The maximum value, you will confirm that the isoprofit line is parallel to the equation for the constraint, that is 3P plus 6Q equals to 900. The solution yields two optimal, which are 50 units of P and 125 units of Q, 100 units of P and 100 units of Q. The maximum contribution in both cases is 2,400 naira. D. Infeasibility. The problem of infeasibility occurs when the constraints are inconsistent to the extent that no feasible solution exists for the problem. In a graphical approach, this happens when the feasible region is empty. In a simplex method, infeasibility is indicated by the presence of artificial variable in the final solution. E. Maximize Z equals to 20n plus 30m, 2n plus m less than 40, 4n minus m less than 20, n greater than 30, n, m greater than 0. F. Solution 2. You should confirm that the feasible regions for the first two constraints are together on one hand, while that of the third constraint is on the other hand, there is no means of combining the feasible regions to derive solution. This is a situation of infeasibility. H. Example 3. Unboundedness. Attempt to obtain the graphical solution to this linear programming problem. Maximize Z equals to 10k plus 20v, subject to 2k plus 4v greater than 16, k plus 5v greater than 15, kv greater than 0. Hi. Duality in linear programming. For every linear programming problem, there is another linear programming problem which is related to it and therefore may be derived from it. In this section, we consider the method of deriving the dual to a given problem. Before you write the dual to an LPP, it is necessary to express it in standard form if it is not so. To ensure it is in standard form, you check that all the variables in the problem is non-negative and all constraints are of less than for maximization problem or all of greater than type for minimization problem. To change to standard form, you may have to do the following. When all variables in the LPP are not non-negative, if a variable is unrestricted in sign so that it is free variable, then you may replace it by the difference of another two non-negative variables, each of which is non-negative. While each of the variables you introduced is non-negative, their difference is free and might be positive, negative, or 0. Duality in linear programming. When all constraints are not with the expected inequalities. If a constraint involves an inequality in a direction opposite to the one expected, you multiply throughout by -1 and change the direction of the inequality. If a constraint involves equation rather than inequality, you replace it by a pair of inequalities in opposite direction and then multiply one of them by -1 to obtain the desired direction of inequality. J. Steps in obtaining dual. To write the dual of a linear programming problem, you follow the steps below. Change the type of the problem. If the original or primal problem is that of maximization, you will formulate the dual problem as minimization problem. Change the variables so as to distinguish dual from primal. For example, if the primal problem uses x1, x2, x3, xn, you may use y1, y2, y3, yn for the dual. Also change the variable that identify of the objective function. Note that the number of variables in the dual equals the number of constraints in the primal. K. Example 4. All constraints with expected sign. Write the dual of the following LPP. Maximize Z equals to 40x1 plus 35x2 subject to 2x1 plus 3x2 less than 60. 4x1 plus 3x2 less than 96. x1, x2 greater than 0. L. Solution 4. Since the primal is maximization, you will formulate the dual as minimization. Let us use Let us use y1 and y2 for the constraint 1 and 2 respectively. Let's also use G to identify the new objective function instead of Z. The constraint value of 60 and 96 for constraint 1 and constraint 2 respectively of the primal become the coefficients of y1 and y2 respectively in the new objective function. That is, the new objective function is minimize G equals to 60y1 plus 96y2. A. In matrix form, the LHS of the primal constraint is bracket 2, 3, 4, 3, x1, x2 for the dual. The transpose of the coefficients matrix is 2, 4, 3, 3 minus the LHS of the dual constraint is 2, 4, 3, 3 y1, y2. The new LHS equation is 2y1 plus 4y2, 3y take 2, 3y1 plus 3y2. B. You then change the direction of all constraint from less than type to greater than type. That is, we now have 2y1 plus 4y2 greater than 3y1 plus 3y2 greater than. The coefficient of the objective function is 40 and 35 for x1 and x2 respectively. These become the RHS values of the constraints in the dual. The dual constraint becomes, by adding the non-negative constraint, the dual of the problem becomes minimize G equals to 60y1 plus 96y2, 2y1 plus 4y2 greater than 40, 3y1 plus 3y2 greater than 35, y1, y2 greater than 0. M. Example 5. Constraint with wrong direction of inequality. Write the dual of the following LPP. Minimize Z equals to 10x1 plus 20x2, subject to 3x1 plus 2x2 greater than 18, x1 plus 3x2 greater than 8, 2x1 minus x2 less than 6, x1, x2 greater than 0. Summary. In a linear programming problem, it is possible to have a situation where there is more than one optimal solution. You can have a situation where the constraints are inconsistent to the extent that no feasible solution exists for the problem. And there can be situations when the feasible region is infinite, such that there are infinite feasible solutions. For every linear programming problem, primal, there is another related linear programming problem, dual, which may be derived from it. To derive the dual, you change the type of the problem. Use another variable. Use constraint values of the primal to form the coefficients of objective function in the dual. Use column of the coefficients in the constraint in the primal to form the row of the constraint in the dual. You reverse the direction of the inequalities. Use the coefficients of the objective function of the primal to form the constraint in the dual, and add the non-negative constraints as usual. End of study session 4. Thanks for listening.